Welcome to this online training about the high bandwidth memory found in certain Altera FPGAs. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. In this training, you will learn about high bandwidth memory, or HBM, a next-generation high-speed memory technology built directly into Altera Agilex 7 M series, Altera Stratix 10 MX, and select Altera Stratix 10 DX devices using System-in-Package, or SIP, technologies. You'll see why this integration offers a very compelling solution for many of today's most demanding applications. You'll learn about the features of the hardened HBM controller found in these devices and how to parameterize and integrate the HBM IP into an Altera Quartus Prime project. Finally, you'll learn about HBM controller efficiency and how to optimize and measure the efficiency of your own HBM interface design. As you proceed through the training, it is recommended that you have basic familiarity with memory technologies such as DDR memory and the ARM AMBA4 AXI or AXI4 interface standard. AXI4 is the primary interface standard used for accessing the HBM from the FPGA core, so understanding the signaling used will make it much easier to implement a design. See the AXI4 specification from ARM, linked here, to learn the details of this interface. Here is the agenda for this training. In the first part of the training, you are introduced to the HBM standard, including a look at its unique features and its architectural design. In Part 2, you learned about the features of the hardened HBM controller, or HBMC, and the user interface required from your design to communicate with the controller. In this final part, you'll see how to implement the interface in the Altera Quartus Prime software, and how to measure and optimize the performance and efficiency of the interface. Note that when HBM is mentioned in this training, it is referring to both the HBM2 and HBM2E standards, unless otherwise noted. Also note that the architecture and implementation of the HBM2 found in Altera Stratix 10 MX devices and Altera Stratix 10 DX devices is similar, unless otherwise noted. References to Altera Stratix 10 MX devices will also refer to Altera Stratix 10 DX devices. Now let's look at how to implement the HBM2 or HBM2E IP in an Altera Quartus Prime Pro Edition project. To use the HBM in a design, make sure to target a part that includes it. The part number decoding for current devices that include HBM is shown here. Note that not all Altera Agilex 7 M series devices include HBM2E. These parts numbers start with AGMA or AGMB. Also note that the 2100 logic element variant of Altera Stratix 10 DX devices is the only variant that includes HBM2. Once you've chosen a device, to add the high bandwidth memory IP to a project, the target device for the project must be set in the new project wizard or selected from the device settings in the assignments menu after a project is created. Once the target device is set correctly, the HBM IP can be added to the project either from the IP catalog in the main Altera Quartus Prime software or as a component in Platform Designer. Double-click the IP core to open its parameter editor. We'll now go through parameterizing the HBM2 IP for Altera Stratix 10 MX devices. The parameters are identical for Altera Stratix 10 DX devices. If you are targeting an Altera Agilex 7 M series device with HBM2E, skip to the next section of the training. The HBM2 IP is configured using the familiar IP parameter editor. Here is the General tab of the editor. At the top of the tab, select basic options for the memory. First, select whether this instance is for the UIB at the top or bottom of the device. If both the top and bottom stacks are to be implemented, 2 instances of the HBM2 IP are required. Below, in the HBM interface section, enable interfaces to the controllers for the individual channels of the stack. Remember that each die in the stack is made up of 2 channels, and that the same 8 channels are used to access both the lower and upper 4 dies of the stack in an 8-high memory. For each interface enabled here, an additional controller tab will appear in the parameter editor, since each channel controller can be configured independently from the others. There are additional options for each of the 4 pairs of channels. The first 2 pairs are shown here. The options for channels 4 through 7 are the same. First, select the interface protocol to use to access each pair of channels, either the default AXI4 interface or the optional Avalon memory mapped interface. If AXI4 is used and both channels in the pair are enabled, select whether the 4x4 soft logic switch should be included for that pair of channels. Remember that this switch allows 4 AXI4 managers in the user logic to share access to the 4 pseudo channels of the selected pair of channels. If the switch is included, the options on the right are enabled. Here you can set the maximum number of transactions an AXI4 manager can issue to a particular pseudo channel before it must hand access to a different manager. You can also optionally select an honored manager that has first access to a pseudo channel if multiple managers are trying to access that pseudo channel at the same time. Lower down on the General tab in the Communication Interface section, specify options for interfacing with the controller. This includes the use of the soft logic adapter mentioned earlier for controlling the AXI4 handshaking signals. The first option back pressures the incoming read data or write response to a user logic AXI4 manager when the manager asserts R ready or B ready, respectively. This option must be enabled if the 4x4 switch is used on any channel pair as just discussed. The second option adds up to 2 cycles of latency before the valid signals are asserted by the AXI4 manager when it receives AW ready, AR ready, or W ready from the controller. If this option is enabled, the third option becomes available to select where the registers for this latency should be placed, either within the IP or manually outside the IP. The choice of location will depend on which will work best to meet timing requirements. Below that are the thermal throttling options. Set the minimum temperature of the memory stack where the interface should start throttling performance, and select the throttling ratio. The higher the throttling ratio, the less often the ready signals are enabled, but this can help reduce the temperature of the stack. In the clock section, specify the clock speed you want to run the memory. The maximum memory clock frequency you can select is based off the speed grade of the device. Below that, select to use the recommended PLL reference clock frequency for the IP for best performance, or specify what frequency you will provide. Next, set the clock frequency for your user logic. This speed is also based on the device speed grade and your ability to close timing in the design. Note that the minimum speed of your design logic must not be less than 1/4 of the HBM2 memory clock. Finally, if you are going to generate the HBM2 example design, you can specify a separate reference clock frequency for it, or use the recommended frequency for best performance. We'll look at creating the example design a little bit later. This table shows you the clocking options for the HBM2 stack based on the speed grade of the selected target device. As mentioned, the minimum core clock frequency is 1/4 of the interface frequency. It can be set faster as long as the design is still able to meet timing. After the General tab is the FPGA I/O tab. This tab only has a single option. Select whether on-chip termination should be used or not with the input reference clock used for the memory PLL. The I/O standard for the clock input must be LVDS. For each controller enabled on the General tab, a new Controller tab becomes available. The available parameters on each controller tab are the same for all 8 channels, but can be unique for each. To make it easy to copy settings between controller tabs, set the Is Clone Of option to the already configured controller tab you want to copy. Controller parameters correspond to the controller options discussed earlier. If Avalon is used as the interface protocol instead of AXI4 for a particular pair of controllers, there is no separate sideband interface. As such, the first options available on this tab enable additional auto precharge and command priority control signals to be used along with the main Avalon interface to control these features. Next, enable the reorder buffer to enable command reordering when memory accesses have different transaction IDs. Enable thermal throttling for this channel based on the junction temperature and throttle ratio selected on the General tab. Adjust the address element ordering for optimal accesses depending on the type of data being transferred. If the interface protocol is AXI4, set the mode for user-controlled read and write auto precharge policies. Either force auto precharge immediately after a read or write operation, or the hint option to let the controller decide the best time to issue the precharge command. Enable the power down option to shut down this channel if it has been idle for a long period of time. Finally, you can set the refresh mode, allowing the controller to completely control memory refreshes or choose to manually control refreshes to the entire memory stack or to particular banks. More options are available in the Data Configuration section of the Controller tab. First, choose to allow for burst transfers greater than 2. When this is enabled, the AXI4 read and write length signals are used to specify the number of transfers within the burst up to the maximum burst length specified here. This option is available only if the 4x4 switch is disabled for the channel pair, and if the following option for using pseudo BL8 transfers is disabled. Recall that pseudo BL8 transfers are performed as a fixed burst length of 2 32-byte transfers, so using pseudo BL8 prevents burst transfers with a length greater than that. Next, set the AXI4 data bus width between the user logic and the controller based on the data width per pseudo channel. This option defaults to 256 bits, corresponding to a total of 512 bits on the user logic side for the separate read and write channels. The width can be increased to 288 bits if ECC and data masking are not used. The extra data bits appear on the AXI4 R user data, W user data, and W user strobe signals. If you want to use ECC, the width must be set to 256 bits. Enable ECC using the option below the width setting. Remember that data masking and ECC cannot be used simultaneously because the same signals are used for both. If you want to use data masking, ECC must be disabled and the Write Data Mask Enable option must be turned on. The Diagnostics tab includes options for testing the functionality and efficiency of the HBM2 interface. In the Traffic Generator section, specify options for the traffic generator created for the HBM2 example design as a way of testing memory accesses. Example design options will be discussed in a moment. You can set the traffic generator to send a default memory access traffic pattern to the memory controller. The Mix Traffic option causes the controller to send out a mix of different traffic patterns using either sequential or random addressing instead of strictly sequential. To test memory accesses that use different transaction IDs, enable the next highlighted option. We'll look at the caveats of using this option later when discussing controller efficiency. Next, choose options for creating and controlling custom traffic patterns to the memory. a custom pattern set up in the traffic generator can be sent using the External Memory Interface Debug Toolkit if the configuration module is enabled, or by configuring and controlling the traffic generator through an optional exported Avalon memory mapped agent interface. Enabling the option to run the user-configured traffic stage automatically runs a user-configured traffic pattern to the memory after reset instead of the default pattern. The final traffic generator options control whether HBM simulation model transaction messages and AXI4 interface transaction messages appear in the output of a simulation. In the Performance section, choose to enable an efficiency monitor and, optionally, have the traffic generator send a specific, highly efficient traffic pattern to test the overall controller efficiency. The efficiency monitor is only available for burst lengths of 1 or 2, meaning BL4 and pseudo BL8 only. Enabling the option to allow burst lengths greater than 2 on any channel tab prevents the use of the efficiency monitor. To further test efficiency, the traffic generator can be set into a high efficiency mode where returning read data is not matched to the data written to see what efficiency can be achieved. Again, we'll look at the use of these options in more detail later in the training. Finally, enable the In-System Sources and Probes option for debug access to common debug signals, including the ability to view the status of memory calibration and the traffic generator. On the Example Designs tab, choose what files will get generated when you generate an example design. An example design provides a complete design for testing in hardware or simulation. Since the user logic may not be created yet, the example design includes a traffic generator, discussed earlier, that can be used to test memory accesses. Choose to create the example design files for simulation, synthesis, or both, along with the HDL format for the simulation example design. The simulation and synthesis options enable the generation of all the files for the example design. If the simulation or synthesis options are disabled, generating the example design still creates a .qsys file for that design, but instead of the complete file set, it generates a tickle script that can be run manually later to generate the rest of the files. Now we'll go through parameterizing the HBM2E IP for Altera Agilex 7 M series devices. Some options are similar to the options available for Altera Stratix 10 MX devices, so any specific differences will be highlighted. But if you are targeting an Altera Stratix 10 MX device, you can skip this section of the training. The HBM2E IP is configured using the familiar IP parameter editor. There are only 2 tabs, but controller channel subtabs are added as shown on the General tab as channels are enabled. For each channel enabled, an additional channel tab will appear, since each channel controller can be configured independently from the others. Remember that each die in the stack is made up of 2 channels, and that the same 8 channels are used to access both the lower and upper 4 dies of the stack in an 8-high memory. Near the top of the General tab, specify the clock speed you want to run the memory. The maximum memory clock frequency you can select is based off the speed grade of the device. Below that, select to use the recommended PLL reference clock frequency for the IP for best performance, or disable the checkbox on the left to specify what frequency you will provide. Finally, select whether resetting the memory simply resets it, or if the UIB will also be recalibrated on reset. This table shows you the clocking options for the HBM2E stack based on the speed grade of the selected target device. The parameter editor offers multiple options for speeds up to these maximums for each speed grade. You may notice that there is no parameter for selecting whether to use the top or bottom HBM2E stack in the device. This is because this selection is based on the selection of the use of the top or bottom NOC and the locations of the INIUs and TNIUs that connect the FPGA core to the memory stack. So to select the top or bottom stack, physical location assignments must be made after the IP is synthesized, but before place and route. The options for doing this are listed here. The first option is to select the locations of the NOC and HBM UIB PLL reference clock pins, choosing the pins that drive either the top or bottom NOC and memory stack. This is device specific and can be set manually in the .qsf file or by using the pin planner. The other method focuses on the configuration and placement of the elements that make up the NOC. When creating a design that uses the NOC assignment editor is used to specify a number of options for the implementation. As shown on the left, this includes the grouping of NOC design elements, including the INIUs and TNIUs. A maximum of 2 groups can be designated in the tool, so all elements in the same group will be associated with either the top or bottom interconnect, depending on their physical placement assignments. After grouping the INIUs and TNIUs, the interface planner is used to find legal physical locations for these elements. Selecting a legal location for an element, such as the HBM controller, forces other elements of the same IP instance or NOC assignment editor grouping to be placed in locations that use either the top or bottom NOC and memory stack. You can see in the example on the upper right that there are 2 legal locations for the controller, representing the top or bottom stack. Once the controller is placed, the legal locations generated for the INIUs, as shown in the bottom right, will be restricted to the NOC at that edge of the device. To learn more about the NOC design flow and how to use the NOC assignment editor and interface planner as part of that flow, use the NOC user guide and e-learning linked at the end of this training. Getting back to the parameter editor, for each controller enabled on the General tab, a new Channel tab becomes available. The available parameters on each Channel tab are the same for all 8 channels, but can be unique for each. To make it easy to copy settings between channel tabs, set the Is Clone Of option to the already configured channel tab you want to copy. For controller options, first, you can adjust the address element ordering for optimal accesses depending on the type of data being transferred, as discussed earlier. Next, for user-controlled auto precharge, enable the option and set the mode for user-controlled read and write auto precharge policies. Either force auto precharge immediately after a read or write operation, or the hint option to let the controller decide the best time to issue the precharge command. Recall that user-controlled auto precharge is requested with the AXI4 user sideband signals when performing a read or write transaction. Optionally, enable the power down option to shut down this channel if it has been idle for a long period of time. In the next section of the Channel tab, you can enable thermal throttling for this channel. When enabled, set separate throttling ratios for 2 high temperature ranges, between 85 and 94 degrees Celsius, and for 95 degrees Celsius and higher. The higher the throttling ratio, the less often the ready signals are enabled, but this can help reduce the temperature of the stack. In the Data Configuration section, choose whether to allow pseudo BL8 bursts, which will transfer 64 bytes of data across 2 BL4 transfers of 32 bytes each. Also, set the AXI4 data bus width between the user logic and the controller based on the data width per pseudo channel. When set to 256 bits, a total of 512 bits is used for the separate read and write AXI4 channels. The width can be increased to 288 bits if ECC and data masking are not used. The extra data bits appear on the AXI4 R user, W user, and W strobe signals and can be used for additional data or a user-defined ECC scheme. If you want to use ECC from the controller, the width must be set to 256 bits. The data mask pins to the memory are used to transfer the ECC data. Remember that data masking and ECC cannot be used simultaneously because the same signals are used for both. Finally, for each pseudo channel, specify that pseudo channel's estimated bandwidth, hit rate, and read ratio. This information will be used by the power analyzer if an early power estimation is performed. On the Example Design tab, choose options for a generated example design. Since the hard NOC is required to access the HBM2E stack, many of the options here configure the NOC for this access. It's a good idea to configure and generate the example design for simulation and hardware testing, since it sets up both the memory and the NOC. You can then adjust the design for your own use. See the HBM2E IP Design Example Quick Start Guide linked at the end of this training for details. First, specify the reference clock frequency for the NOC clock control IP. This IP is automatically included in the example design to clock the NOC itself, so the reference clock frequency is already set. If you are customizing the example design, uncheck the box and adjust the frequency. Next, choose how traffic generators for each channel will access the memory. Recall that initiator units, or INIUs, are AXI4 subordinates accessed by AXI4 managers in the FPGA core fabric. The INIUs in turn access the target units, or TNIUs, on the other side of the NOC to access the memory stack. In the example design, the user logic that accesses the stack is a set of traffic generators. By default, each traffic generator accesses a particular pseudo-channel connected through a single dedicated INIU. However, if all 8 channels are enabled, a 16 to 16 crossbar can be implemented in the FPGA fabric to allow any traffic generator access to any pseudo-channel connected through any INIU. This provides more flexibility, but there is more of a possibility of contention between multiple traffic generators trying to access the same channel or pseudo-channel. The next highlighted option is AXI4 Lite support. As discussed earlier, an AXI4 Lite interface is used as a sideband interface to access the memory stack's control and status registers for features such as temperature readouts and the status of calibration. This interface must be enabled in the example design. There are 2 options for it. Either an additional, dedicated INIU can be added to the NOC, bringing the number of INIUs to 17 if all 8 channels are enabled. Or AXI4 Lite access can be shared with the existing INIUs. If sharing is selected, AXI4 Lite access is multiplexed with one of the 4 standard AXI4 interfaces used for each pair of channels, as shown. Next, choose an option to enable or disable the use of the fabric NOC. When enabled, the AXI4 read data channel is doubled to 512 bits wide, and M20K on-chip memory blocks in the fabric are used for temporary read data storage. This improves performance by moving any congestion caused by the incoming read data away from the periphery of the device. The options available enable this fabric NOC with the additional option to set the write data channel to 512 bits wide as well. You can also choose whether to share clocks between the read and write channels, or use separate clocks to improve either read or write speeds, depending on the application. The NOC bridge hardware frequency option sets the clock used to drive the other 256-bit wide channels when the 512-bit wide option for both the read and write channels is selected to enable the fabric NOC. To learn more about the use of the fabric NOC, see the NOC user guide and training linked to at the end of this training. The other clock options for the example design set the core clock frequency for driving the traffic generators and INIUs in the core fabric, and the reference clock frequency for the PLL that generates this clock. The maximum frequency that can be set is again based on the speed grade of the targeted device. See the user guide for these values. Below the clock settings, the NOC read and write bandwidth and transaction size options indicate the anticipated bandwidth and transaction sizes based on the other settings specified in the parameter editor, and assuming the most optimal placement of the INIUs and TNIUs in the device. These values can be set for each INIU to TNIU connection using a tool called the NOC assignment editor, used specifically for configuring the NOC. Again, see the NOC user guide and training for details. The remaining example design options are shown here. Choose the type and length of traffic pattern the traffic generator should run during a simulation, and optionally enable performance monitor logic on all channels to generate metrics on read and write transactions. To learn more about the performance monitor, see the on-chip debugging for external memory interfaces training for Altera Agilex FPGAs and the performance monitor IP user guide, both linked here, as well as the HBM2E design example user guide linked at the end of this training. We'll look at how to configure the example design to maximize performance later. Next, choose what files will get generated when you generate the example design. Choose to create the example design files for simulation, synthesis, or both, along with the HDL format for the simulation example design. The simulation and synthesis options enable the generation of all the files for the example design. If the simulation or synthesis options are disabled, generating the example design still creates a .qsys file for that design, but instead of the complete file set, it generates a tickle script that can be run manually later to generate the rest of the files. Now let's take a look at how to analyze the performance and efficiency of the interface implementation. To understand interface efficiency, you must first understand the available bandwidth for the HBM2 or HBM2E interface. The maximum and effective bandwidth can be calculated as shown here. Given 128 bits of DDR data running at the maximum supported speed of 1 GHz in Altera Stratix 10 MX devices and 1.6 GHz in Altera Agilex 7 M series devices, the maximum bandwidth per channel would be 32 GB per second or 51.2 GB per second, respectively. Multiply this by 8 for the 8 channels to get a total maximum bandwidth of 256 GB per second and 409.6 GB per second. Effective bandwidth is based on how efficiently the controller performs data transactions. The HBMC has a potential efficiency of 90%, providing an effective bandwidth of about 230 GB per second for Altera Stratix 10 MX devices and 369 GB per second for Altera Agilex 7 M series devices. But what exactly is controller efficiency? It is a measurement of how much of and how often the data bus is being used to transfer data. So why do we care about this? By analyzing and understanding controller efficiency, we can get an idea of how efficient read and write commands are being translated between the user logic interface and the HBM stack accesses through the PHY. If this translation is efficient, more transactions can be scheduled, creating a more efficient overall interface. Efficient command scheduling, handled by the controller, can help with this as well. How the HBM stack is accessed, as well as the controller configuration, affect controller efficiency. Here are the main factors on the memory side. First, sequential memory accesses are always more efficient than random accesses to different locations in memory. Random accesses require additional pre-charge and activate commands from the controller that affect efficiency. Along with this, sequences of transactions that switch between reading and writing can also have a big effect on efficiency. Switching between reading and writing incurs a bus turnaround penalty that slows down the interface. The AXI4 interface to the HBM stack does support concurrent writes and reads, which can help in mitigating this penalty. Bank group access can also be a factor. Recall that different bank groups are addressed using bits 2 and 3 of the 4-bit bank address. DRAM memory, such as the memory used for DDR4 and HBM, can use short, more efficient timing requirements when different bank groups are accessed by a controller. If memory in the same bank group is accessed, the memory must use longer timing requirements. Using the long timings will negatively affect efficiency. Memory refresh and pre-charge policies also affect efficiency. The interface is more efficient if refreshes can be postponed until absolutely necessary, instead of just refreshing all the time. Remember that only Altera Stratix 10 MX devices have an option for user-controlled refresh, so try to minimize and postpone refreshes as much as possible if using this feature. Intelligent pre-charging also improves efficiency, especially with random transactions, if the appropriate area of memory can be pre-charged ahead of when it needs to be accessed. For auto pre-charge policies, use the forced option if you'll be performing many random transactions to different memory locations. Use the hint option for sequential transactions so the controller can choose the best time to issue the pre-charge. On the controller side, many of the features we've discussed affect efficiency. Of course, using pseudo BL8 burst transfers instead of BL4 keeps more data flowing across the interface. Pseudo BL8 accesses also take advantage of the shorter timing requirements available when accessing different bank groups, as just discussed. If you're using an Altera Agilex 7 M series device, pseudo BL8 transfers are much better at saturating the available bandwidth of the NOC, so use them instead of single BL4 bursts. Efficient scheduling of commands with different transaction IDs also keeps the bus busy. Recall that each read or write transaction is marked with a transaction ID using the ARID or AWID AXI4 signal. Transactions with the same ID must be executed in order, so if all transactions have the same ID, command reordering is not possible. However, if multiple IDs are used, transactions with the same ID must still be executed in order, but transactions with different IDs can be interspersed between them. This lets the controller issue commands in the most efficient order. For clocking the design, the speed of the user logic versus the speed of the memory has an effect on efficiency. Try to operate the user logic at a speed that is as close as possible to the memory frequency. Of course, the faster the user logic is running, the more difficult it will be to close timing on the design. Finally, recall that high memory die temperatures cause the controller to adjust how the stack is accessed until the temperature is reduced. This is done in two ways. First, at temperatures above 85 degrees Celsius, the controller issues refresh commands more often. Second, if thermal throttling is enabled as discussed earlier, ready signals are disabled more often based on the throttling ratio selected, reducing data bandwidth. These effects can be mitigated by monitoring the temp register of the memory stack, accessed via the APB or AXI4 Lite sideband interface, depending on the targeted device. The temp register indicates what the current refresh rate is based on the hottest die in the stack. Use this information to adjust how the stack is accessed accordingly before automatic throttling occurs. Besides controller efficiency, both the efficiency monitor and performance monitor IP, discussed in more detail in the next section, report on read latency. Read latency, measured in user logic clock cycles, is the total round-trip time from when the user logic, which may be the example design traffic generator, issues a read command on the read address channel to when valid read data is available on the read data channel. Read latency is made up of multiple parts. The first is the command latency from when the user logic issues the read command to the command being translated and sent to the memory stack. Next is the memory read latency, the number of cycles for the memory stack to return data to the controller. The final factor is the latency from when the data arrives at the HBMC to when the data is available back at the user logic. In an Altera Agilex 7 M series device, the performance monitor IP also includes the latency for commands and data through the NOC switch matrix. For Altera Agilex 7 M series devices, the NOC can play a significant part in optimizing performance and memory access efficiency. Here are a few NOC-related considerations to take into account. First, since the NOC is required to access the HBM2E stack, inherently, there will be added latency in accessing the memory. However, the higher speeds available for the NOC and the memory stack can mitigate this. When creating a design that includes the NOC, the placement of the INIU on the fabric side of the NOC relative to the TNIU on the periphery side of the NOC that accesses the memory stack can be selected by the designer. The closer the INIU is to its connected TNIU, the less horizontal data transfer through the switch matrix of the NOC is required. Since this reduces latency through the NOC, try aligning INIUs and their associated TNIUs as closely as possible. To measure the amount of latency through the NOC, use the performance monitor IP mentioned earlier, implemented in an example design. See the NOC user guide, the HBM2E design example user guide, and associated trainings, all linked at the end of this training, for details. Next, if you're starting your design by generating the example design, choose the appropriate option in the parameter editor for mapping initiators to targets through the NOC. The one-to-one full address connection option is required if anything less than all 8 channels are enabled. But when this option is selected, each INIU only has access to the single pseudo channel it's connected to via its connected TNIU. If all 8 channels are enabled, selecting the 16x16 crossbar option lets all INIUs have access to all pseudo channels. This is useful if you have multiple AXI4 managers, such as the traffic generators created for the example design, that need access to the same pseudo channels. If you can, it is recommended to make use of the Fabric NOC feature. Recall that this feature increases the read and write data paths of each INIU connection to 512 bits, maximizing the bandwidth access to and from the NOC. It also enables the use of available M20K blocks in the fabric to buffer incoming read data from the memory stack, reducing congestion at the periphery. Finally, using this feature creates independent clocks for the NOC and the fabric core. This allows the NOC to run as fast as possible, while the core user logic can run at a more manageable speed that may make it easier to close timing. Finally, let's look at how to generate and use example designs to measure the performance and efficiency of an HBM2 or HBM2E implementation. To measure the efficiency of the interface implementation, enable either the Efficiency Monitor on the Diagnostics tab or the Performance Monitor IP for an example design, depending on your device. You can see here where each of these options are in each of the parameter editors. To measure efficiency of the memory stack, either the Efficiency Monitor or the Performance Monitor IP watches transactions on the AXI4 interface for each pseudo-channel. The Efficiency Monitor or Performance Monitor IP keeps track of when the HBMC issues its ready handshaking signal on the address read, address write, and write data channels. The assertion of ready indicates how quickly transactions are being processed by the controller. The Efficiency Monitor or Performance Monitor IP calculates the ratio of the total number of accepted data transactions versus the total time for a transaction. It then scales the calculation by the ratio between the core and the HBM2 clock to provide an overall efficiency percentage calculated using the formula shown here. Note that the Performance Monitor IP has the advantage of being able to not only report overall efficiency of the interface, but also break down its analysis into separate efficiency measurements for read and write transactions, as well as the efficiency of each individual connected pseudo-channel. Let's look at using the Efficiency Monitor to calculate the efficiency of an HBM2 implementation in Altera Stratix 10 MX devices. If you're creating an HBM2E implementation in an Altera Agilex 7 M series device, skip to the next section. To simulate your HBM2 interface design for high efficiency, configure the IP parameters to the values shown here and create the simulation example design with the Efficiency Monitor enabled. The listed settings allow the design to run as fast and as efficient as possible. On the General tab, set the memory and core clocks to their fastest speed supported for your selected device speed grade. Use the default recommended PLL clock reference frequencies. On the Controller tab, turn off the reorder buffer. Remember that the reorder buffer adds latency to reorder read data from different transaction IDs. Set the address reordering, pre-charge policy, refresh policy, and use of sudo BL8 burst transactions as shown. These settings correspond to the most efficient controller settings based on the factors just discussed. On the Diagnostics tab, set the traffic generator to use the default traffic pattern. Also enable the traffic generator to issue commands with different transaction IDs. Since the reorder buffer is disabled, the controller can efficiently reschedule memory accesses with different transaction IDs without the data reordering latency penalty. It is possible for data mismatches to occur with these settings, but these can be ignored for the purposes of measuring efficiency. Of course, the efficiency monitor should be enabled, along with the efficiency traffic pattern, but also enable the data check option. When this option is enabled, the traffic generator does not perform read validation of written data. As such, the traffic generator can issue more access commands sooner. Of course, data mismatches may occur, but again, this is okay for the purposes of testing efficiency. Along with this data checking, make sure the read count and write count values are equal, and set the sequence option to sequential instead of random. Again, the idea is to avoid any delays caused by reordering, so if read or write commands are issued in order and processed in order, this will correspond to the most optimal efficiency for the design. Here's what the generated simulation example design looks like with the efficiency monitor and only channel 0 of the stack enabled. Example design generation automatically includes the simulation memory model, the simulation checker block, and the traffic generators for each pseudo-channel. See the user guide for details on running a simulation. Now let's look at the settings to use to create a performance-optimized example design for an Altera Agilex 7 M-Series device. For performance testing in an HBM2E implementation, generate an example design for synthesis that includes the performance monitor IP and run the design in hardware. The performance monitor IP can be accessed through simple control and status register access, or using the pmon tickle scripting library in the system console debugging tool. See the performance monitor IP user guide linked here for details. For performance measurements, set HBM2E IP parameters appropriately. First, make use of the fabric NOC option, increasing the data path width to the NOC INIUs to 512 bits allows them to be run at their highest allowable frequency. For -1 speed grade devices, this is 660 MHz. Set this for the NOC bridge hardware frequency option in the example design settings. If you are only interested in optimizing read performance, you can instead keep the write data paths at 256 bits and set just the read data paths to 512 bits. When the Fabric NOC option is enabled, a separate independent clock is generated for the core logic. The IP user guide details the specific core clock frequencies that are compatible with the maximum bridge hardware frequency for each speed grade. The guide also highlights which of these compatible frequencies will be the easiest for closing timing. For example, for the bridge hardware frequency of 660 MHz in -1 speed grade devices, 440 MHz is recommended, though the core can be run at faster or slower speeds if desired. Again, see the user guide for supported frequencies. Next, set the initiator to target NOC mapping option to use the 1-to-1 full address connection instead of the 16x16 crossbar. The 1-to-1 connection ensures that each pseudo-channel receives purely sequential accesses from each traffic generator. The crossbar, which again can only be used if all 8 channels are enabled, allows for random accesses, which greatly reduces the efficiency of the interface. Efficiency is reduced so much when the crossbar is used that even without the fabric NOC enabled, throughput through the NOC can be saturated. Finally, since efficiency is so closely tied to INIU physical placement, make sure that you use explicit location assignments in your project to place the INIUs as close as possible to the appropriate TNIUs as shown earlier. The optimal placement also splits the INIUs evenly to the left and right halves of the device to help minimize congestion. The HBM2E Design Example User Guide provides an example of specific location assignments for connecting to a memory stack at the top edge of the device. But you can always use the Interface Planner tool to graphically place and check the legality of INIU location assignments for optimizing placement using the NOC at either the top or bottom edge. See the NOC User Guide and the associated training linked at the end of this training for details on using Interface Planner. Here is what the generated example design looks like with the performance monitor in place. While the NOC itself is not shown, connections to and from the NOC initiator IP, which establishes the connections between the user logic and the NOC INIUs that connect through the NOC to each pseudochannel, and the NOC clock control IP, which clocks the NOC directly, are automatically included when the design is generated. The test engine IP acts as the traffic generator user logic for each pseudochannel and can be used for when the design is synthesized into hardware or for simulation. Learn more about the test engine IP from its user guide, linked here. This concludes the final part of this training. If you missed either of the previous parts, you can register for them for free at the links shown here. To learn about additional resources available to help you with using high bandwidth memory, continue to the next slide. For more information about HBM2 and HBM2E in Altera Stratix 10 MX and Altera Agilex 7 M series devices, see the online resources listed here. The HBM IP user guides go into detail on the architecture of the memory in these devices, as well as all aspects of implementation, including IP parameterization, IP signaling, clocking, and simulation. The design example user guides walk through the entire implementation flow, including design simulation, and how to use the design example for performance testing. If you will be using the HBM2E DRAM found in Altera Agilex 7 M series FPGAs, the NOC documentation and associated training go through all the details of how to include the NOC in a design, which is required for an HBM2E implementation. Finally, the ARM AMBA4 AXI specification describes in detail the standard interface required for accessing the HBM found in these devices. Altera offers many options for learning about our FPGA products and for training on their use. The Altera FPGA YouTube channel contains a number of 5-minute quick videos along with longer, more in-depth training. The Altera FPGA training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, you can register for over 300 e-learning courses made up of narrated slides presented in an interactive player, some of which include labs and demos. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person at a local office or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Altera FPGA provides many self-help resources. Check out the landing pages, accessed from the main Altera website, that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Altera FPGA application engineers. One more thing. You will receive a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on the high bandwidth memory found in Altera FPGAs.